Hello, everyone. Here we are, 441. So the last section of chapter 4, and we're going to be calculating the area between two curves. And we're going to do it through this example, and I'm going to talk you through it, talk about some of the main points here about how we can use technology, not technology, where it comes from, because you want to understand all parts to this from all the different angles so you can tackle the problem as it gets more complex. So let's find the area between two curves below. And the two curves we're going to look at is f of x equals x plus 6 and g of x equals x squared. So if I graph these, g of x being x squared as a parabola, that would look something like this as a sketch. And x plus 6, go up 1, 2, 3, 4, 5, 6, up 1 over 1. Now I know it's not going to be perfect, but it will look something like this. So that's f of x, and that's g of x. And this is just a sketch. I know you could make the graph more exact, but kind of ran out of room when I did that, but that's okay. So we want to find the area between the curves shaded by this region here. Now, how do we do that? Now, recall that the integral represents the area under the curve. So if we were to break this up and say, let's just look at the area in the curve of just f of x. So recall that the area under the curve is represented by an integral. Now, if we just look at f of x here, and I'll try to write a little bit darker, we want to find the area in the curve from this point, which we'll call A for now, to this point B, we'll call B for now. If we just looked at f of x, well, imagine this parabola is not there. What that would look like is it would find the area under the curve of this entire almost trapezoid. We'll do side to sides like that. And that's f of x, that shading left and right. And then if we were to find the area of just g of x, which is this parabola, where the area under the curve from A to B would actually be represented by this region here, which I'm doing with these up and down marks. So notice that if we wanted to get the area of the shaded region, if we found the area under f of x, this entire trapezoid, that would give us all of this, and then we subtract off this space here. If we minus this space here, that's the area under the curve of g of x, well, we'll be left with this area here, which is the area that we were intending. So maybe if we wrote this in an equation to help you see this, so we could find the area under the curve by doing the integral from A to B of f of x dx minus the integral from A to B of g of x dx. By subtracting those two integrals, we'd be left with the net area. Now, with our understanding of properties of integrals, we can actually combine this and write that this is just equal to the integral from A to B of, and notice I put all this in parentheses, f of x minus g of x with respect to the changes in x. And there is right there, that's how you find the area of the curve between, or the area between two curves, where what you'll notice is what can we talk about f of x as? F of x we can see as the upper function, and g of x will be subtracting the lower function. And that we can use to find the area between two curves. Looking at the area of the upper function minus the area of the lower function will result in a net area of that region between the two. So let's apply this to this problem here and talk about what that means. So in this problem here, we need to find A and B, which notice, what are A and B? Notice that A and B are the intersection points. Intersection points of the two curves. Okay. Now, we can find the intersection of the points between two curves two different ways. Way one is by hand, which you should always know how to do things by hand. So I'm going to zoom out because I want to try and keep that picture for us. So by hand, we would set the equations equal to each other. So we'd set x plus 6 equal to x squared. Focus that a little bit, might be too zoomed out. We're solving for x now. We get everything to one side and get x squared minus x minus 6 equals 0. That'll factor as x minus 3x plus 2, in which we'll get that these intersect at x equals 3, negative 2, which is great. So we know that our curve will go from negative 2 to 3. Now, if you want to do it way two, which is definitely going to come in handy because we don't always have the tools to do it by hand, and that's using the graphing calculator. Okay. Now, how would the graphing calculator look? So you would go and put these functions into y equals. Let me delete what was previously in there. So we have the curve x plus 6 and x squared. Graph them. I might need to zoom out just a tad. Oh, no, I'll be okay. And then right here in blue, we're going to calculate the intersection points of these two curves. And notice how it says first curve, so that's like which function, which we'll just pick the linear line. Second curve, the parabola. And the guess, you want to put the guess closer to where you want. Because notice how there's two intersection points. If you don't pick the guess, it'll be random, which eventually you'll figure it out if you didn't do this anyway. So this intersection point's at negative 2, 4. So it's telling us on the curve that this one's at negative 2, 4. And then if we did that again, calculate the intersection point of the second one. So I'll go to that point, hit enter 3 times, and that's at 3, 9, which is what we got by hand too, of negative 2 to 3. So using graph calculator, we got the intersection points of negative 2, 4, and 3, 9. Okay. Now, I know we can do f of x minus g of x dx to represent the area here, and I understand that you're going to say we can just put this in the equation as x plus 6 minus x squared with respect to x. And I know we know that, and you might be able to do that right now. But one thing I want to talk to you about, because this is a more conceptual understanding of this, is what is this, where is this being represented graphically? And I want to make sure you understand this, because if you can understand this graphically, you're going to have a better idea of understanding this as it applies to different area between the curves, and maybe when you get the volume. Now remember, to get the area of between these two curves, we're talking about integrals, and integrals relates to Riemann sums, taking infinitely many rectangles. Well, if I draw one rectangle here, and I'm going to try to draw it right here, left endpoint, so we're doing left endpoint, it would look something like this between the two curves. We're from the bottom of the curve to the top of the curve and over. Okay. Now, what's the dimensions of this one rectangle? So if we want to find the area of this rectangle, we need length times width. Well, what's the width here? Well, the width is the changes in x. And remember, we're approaching infinitely many rectangles, so that width is going to be the change in x, or in terms of our integral, the dx. So the width for rectangles are the changes in x, with respect to x, the dx, these little tiny widths, still larger than 0, because it has to give us an area, but there are width there. Now, what's the length? What's this distance here? Well, notice if we went from the top of the curve down to 0, this whole thing is the length of f of x. From the top of the curve to 0 would be f of x. And the length from the bottom of the curve to 0, well, if we did a left endpoint rectangle there, that height is at g of x. So by just doing So say if I drew this out here, and we want to go from here to here to help you see this. Oh no, we want to go from here to here. This is what we want. Well, this is g of x, that height. The whole height is f of x, the length when I say height. So what are we left with? Well, the height of this rectangle is f of x minus g of x, and where the height is f of x minus g of x. And notice again that what we got is what we got here, where it's the upper function minus the lower function. But understanding it through rectangles, because again, that's where the integrals are coming from, is this is just one arbitrary rectangle, but really what we're doing when we're taking the integral is we're taking infinitely many of these, with this change of x being infinitely small as our width, and the height of each one being f of x minus g of x at each x location. Okay, so I want to make sure you understand that. Yes, you can do this integral and get to the math and get to the answer quickly. I get that, but it's important you know where this comes from a conceptual standpoint. All right, so let's finish this problem out and be done here. So if we come back to this problem, we're going to do this on a calculator together. So you can't do it on this screen, so get back to the main screen where you can calculate. Use the numerical integration, which is math 9. And we're going from -2 up to 3 of, and follow your parentheses. All right, we already have an outside parentheses here, so you have parentheses, the top function, x plus 6, minus the bottom function, and I didn't put minus myself, which is x squared, parentheses, they have a parentheses, and then with respect to x. What we get here is that the area between these two curves is approximately 20.833. And I don't like to say units squared. I know the book will continue to do units squared, and I guess I don't necessarily agree with it because we don't know what these functions mean in context. I don't necessarily agree, but that's what the book is using. And when the AP exam comes, units squared, I guess, is area. But again, this can represent so many different things. If we're talking about both these functions represent the rate for car, but the area between the cars will be the miles they traveled, that the net miles they traveled between the two. So units squared, units, but just know that there's a units on this answer. But there it is. So putting it all together, area between two curves, where again, this is what you might want to understand, is that A to B are intersection points from the upper minus the lower with respect to x. So, and where that comes from are making these rectangles like here, which we might say are, vertical rectangles, infinitely many vertical rectangles. And we can use the calculator or do it by hand at intersection points. And finally, probably just use the calculator to calculate this. Because could you do this by hand by using the antiderivatives? Yes, you definitely can. And you want to make sure you know how to do that, but it doesn't tell us not any reason not to here, so we'll just use the calculator. Hope that helps. Write down any questions you have. Feel free to email me or ask me if you are still confused on any of this, and I can try and clear it up for you. All right, bye-bye.